Welcome to the deep dive. Today we're taking a plunge into reaction kinetics, chapter 22 to be exact. Our mission is to really demystify all the quantitative stuff, the rates, the orders, the mechanisms, and give you a shortcut to getting it right fast.
And it's a crucial dive because kinetics is how we get past the what and into the how and why of a reaction. Before we get into the new stuff, let's just quickly remember the basics from Chapter 9. We know rate is affected by concentration, temperature, and of course catalysts.
Right, and now we're moving from just knowing what affects the rate to exactly how much.
Precisely, we're getting quantitative.
And to show just how far this field has come, there's this amazing fact in the Before You Start section. We are talking about timescales that are, well, they're almost impossible to imagine.
Oh yeah, forget millisecond.
We're talking picosecond lasers.
Yeah.
That's a pulse of radiation lasting 10 to the minus 12 seconds.
Yeah.
It's so fast you can watch reactions happen before atoms even fully separate.
It's just phenomenal. And that technology let researchers watch something like an iodine molecule, I2, just break apart in a solvent.
And it happened in just 50 picoseconds. But here's where the real chemistry mystery started.
Right, because the iodine atoms didn't recombine as quickly as collision theory said they should. There was a delay.
Which led them to this really controversial idea at the time. They called it the solvent cage.
Exactly. They proposed that the solvent molecules, tetrachloromethane in this case, were physically surrounding the iodine atoms, trapping them.
So like a little cage that stopped them from finding each other again right away?
It was a huge idea.
Yeah.
Because it challenged how everyone thought about random molecular motion. It showed that kinetics is about measuring what's actually happening physically between molecules.
Okay, let's unpack all of this and get into the numbers. The heart of this chapter is moving from theory to measurement, starting with the rate of reaction.
And the definition is pretty straightforward. It's just the change in concentration over time.
So either how fast a reactant is being used up or how fast a product is being made.
Exactly. And because concentration is in moles per decimeter cubed, in times usually in seconds, the units for the rate are fixed. They're always moles per decimeter cubed per second.
Which brings us to the big one, the core formula, the rate equation.
Rate equals K times the concentration of A to the power of M times the concentration of B to the power of N.
Okay, so looking at that equation, what is the number one mistake, the biggest trap that a student can fall into?
Oh, easily. The biggest mistake is assuming that those exponents, M and N, come from the balanced chemical equation, from the stoichiometry.
Right, so if the equation says 2A plus B, you just assume the rate equation is K times A squared times B.
And that is almost always wrong. What's so critical to understand here is that the rate equation is purely empirical. It must be found by doing experiments in a lab.
So wait, stoichiometry tells us the before and after, but not the journey it takes to get there.
That's a perfect way to put it. The stoichiometry is the start and end point. Kinetics is the step-by-step path. There's a great example in the book Reaction 2 in table 22.2. You have NO plus CO plus O2.
Sure.
Stoichiometry suggests all three matter.
But they don't.
Not at all. The experimental rate equation is just. Rate equals K times the concentration of NO squared. CO and O2 are completely absent.
Because they're involved in, what, a much faster step later on?
Exactly. They don't affect the overall timing, so they don't show up in the rate equation.
That disconnect is so important. So let's quickly define the terms from that equation. The order of reaction for reactant A is just its power, M.
Right. And the overall order is just the sum of all those powers, so M plus N.
And these orders are usually whole numbers like 0, 1, or 2. But they can be fractions, right?
They can. The book mentions the decomposition of ethanol, which has an overall order of 1.5. It's rare, but it happens.
Okay, this brings up a really important point about the rate constant, K. Its units aren't fixed.
No, they change depending on the overall order of the reaction. The units for rate are always the same, so the units for K have to adjust to make the equation balance out.
Let's walk through that for a second order reaction. Like H2 plus I2 gives you HI. The rate is K times H2 times I2. How do we find the units for K?
You just rearrange the equation to solve for K. If K equals rate divided by the two concentrations.
Okay, so on top we have moles per decimeter cubed per second.
And on the bottom, you have moles per decimeter cubed times another moles per decimeter cubed.
So one of the concentration units on the top and bottom cancels out.
Right. You're left with seconds inverse on the top and moles per decimeter cubed on the bottom. When you flip that bottom term up, The powers invert.
And you get decimeters cubed per mole per second. dm 3 mole minus 1 s minus 1.
Exactly. And those units are a signature. They tell you it's a second-order reaction.
So we know the equation exists. But in the lab, how do we actually find those crucial exponents, m and n? That's where the graphs come in.
Yes, the graphical methods are key. There are three main ways to visualize the data. Method 1 is plotting rate versus concentration.
And the shape tells you everything.
Tells you everything. If it's zero order, you just get a flat horizontal line.
Meaning the rate doesn't change no matter how much reactant you have.
Correct. The rate is constant. This often points to something like heterogeneous catalysis, where the reaction is happening on a surface.
Oh, so the surface area is the bottleneck, not the concentration of the gas around it.
Precisely. The surface gets saturated. Now, for a first-order reaction, you get a perfect straight line sloping up from the origin.
Double the concentration.
Double the rate. Simple relationship. And for second order, it's not a straight line.
It curves upward.
It curves upwards. And that's because of the squared relationship. If you double the concentration, you don't double the rate.
You quadruple it. 2 squared is 4.
You quadruple it. It's a very powerful effect.
Okay, that's method 1. Method 2 is plotting concentration versus time.
Right. Here, a zero-order reaction gives you a descending straight line. The gradient is constant because the rate is constant.
And for first and second order, they're both descending curves, which sounds a bit tricky to tell apart.
They can be, just by looking. The second-order curve is usually a bit steeper at the start and then has a longer, shallower tail at the end. But there's a much better way.
And this is method 3, which is the ultimate test, especially for first-order reactions, half-life.
The half-life analysis, yes. So the half-life, tat 1/2, is the time it takes for the reactant concentration to fall to half of what it started at.
And here's the magic trick, right? For a first-order reaction.
And only for a first-order reaction, the successive half-lives are constant. They don't change.
The book gives that cyclopropane example. The first half-life was 17.0 minutes. The next was 17.3. The next was 16.7.
I mean, they're practically identical. That is the fingerprint of a first-order reaction. For second order, the half-life actually gets longer as you go.
That constant half-life rule is.
That's a powerful one to remember. Okay, let's switch from figuring out the order to actually calculating the value of K.
The most common way is using initial rates data from a set of experiments. Once you've figured out the rate equation, you just pick one of the experiments. Anyone will do. You rearrange the rate equation to solve for K, and then you just plug in the values for the rate and the concentrations from that single experiment.
And you have to remember to ignore any reactants that were zero order. They're not in the equation, so their concentration doesn't matter for the calculation.
Absolutely. And if you already know it's a first-order reaction because you saw that constant half-life, there's an even faster shortcut.
The equation K equals 0.693 over T 1/2.
Exactly. You can take that half-life of 17 minutes for cyclopropane, convert it to seconds, plug it in, and you get K directly. Super quick.
So connecting this all back, what about temperature? We know higher temperature means a faster reaction.
Right, and that means the value of IC must be increasing with temperature. Why, though? What's happening at the molecular level?
It all comes back to the Boltzmann distribution. At a higher temperature, a greater fraction of the molecules have energy that is equal to or greater than the activation energy, the EA.
So more of the collisions are successful.
Far more. There's a rule of thumb that for many reactions, the rate roughly doubles for every 10 degrees Celsius increase. But the formal relationship is the Arrhenius equation.
That's the one with the natural logs. ln K equals ln A minus EA over RT.
That's the one. And it's incredibly useful because if you plot the natural log of K versus 1 over the absolute temperature, you get a straight line.
And from the slope, the gradient of that line, you can actually calculate the activation energy.
Exactly. It's how we put a number on that energy barrier.
So why do we do all this? Why spend all this energy finding these exponents and rate constants?
Because it's our best tool for figuring out the reaction mechanism, specifically for finding the slowest step.
The rate determining step, the RDS.
The RDS. Think of it as a bottleneck on an assembly line. The whole process can only go as fast as that one slowest step.
And the rule is, if a reactant shows up in the rate equation, it has to be involved in that slow step.
It has to be involved in the slow step or in a fast step that comes before the slow step. Its concentration matters.
And if it's in the overall chemical equation but not in the rate equation,
then it must be reacting in a fast step that comes after the bottleneck. It's waiting for the slow part to finish, so its own concentration doesn't limit the overall speed.
So this data helps us see if a proposed mechanism is possible.
Possible. That's the key word. It doesn't prove a mechanism is correct, but it can certainly prove one is wrong.
Let's use an example. The decomposition of N2O5. The rate equation is just rate equals K times N2O5, first order.
Right. So what does that immediately tell you about the slow step?
It must involve only one molecule of N2O5. It's unimolecular.
Exactly. The slow step must be a single N2O5 molecule just breaking apart. Anything that happens after that is fast and doesn't affect the rate.
And we can work backwards, too. If we're given a mechanism, we can predict the rate equation.
Yes. For the bromination of propanone, if we are told the slow step involves one molecule of propanone and one hydroxide ion.
Then the predicted rate equation must be rate equals K times propanone times hydroxide.
And bromine is nowhere in sight because it's involved in a fast step that comes later. Kinetically, it doesn't matter until the slow part is done.
Okay, final topic, catalysis. We know catalysts speed things up by providing a different reaction pathway.
A different pathway with a lower activation energy, a smaller hill to climb. And we generally split them into two types.
Homogeneous and heterogeneous.
Starting with homogeneous, that's where the catalyst is in the same phase as the reactants. Usually everything is dissolved in a liquid.
And this is often where transition metals come in, right? Cycling between oxidation states.
Yes, that's a very common mechanism.
Yeah.
The classic example is using iron ions to catalyze the reaction between two negative ions, like S2O8 2- and iodide.
Which is normally really slow because the two negative ions repel each other.
Exactly. The iron catalyst, say V3+, can react with a negative iodide ion because they're oppositely charged. That's fast. Then the product of that step reacts with the other negative ion. It breaks the reaction into two faster steps, avoiding that initial repulsion.
We also see this in the atmosphere, unfortunately, like NO2 catalyzing the formation of sulfur trioxide, which leads to acid rain.
A perfect and unfortunate real-world example of homogeneous catalysis.
Okay, what about the other type? Heterogeneous catalysis.
That's where the catalyst is in a different phase. Most often, it's a solid catalyst with gaseous reactants.
And here we have to be careful with our words. It's adsorption, not absorption.
Right. Adsorption is bonding to the surface. Absorption is soaking into the bulk of the material like a sponge. We're talking about adsorption here.
So what's the mechanism? Let's use the Haber process as the example.
It happens in three key stages. First is adsorption. The reactants, nitrogen and hydrogen, land on the iron catalyst surface and form chemical bonds to it.
And this bonding is really important.
It's crucial. The bond to the surface has to be strong enough to weaken the bonds inside the reactant molecules. It helps to break that incredibly strong nitrogen triple bond.
Okay, so they're adsorbed and weakened. Then what?
Stage 2 is the reaction. The absorbed atoms can now move around on the surface and react with each other to form the product, ammonia.
And stage 3 must be getting the product off the surface.
Desorption. The ammonia molecules break their bonds with the catalyst and drift away. This frees up the surface for the next batch of reactants to come in. It's the same principle in a car's catalytic converter.
That's a fantastic overview. So to wrap up our deep dive into reaction kinetics, let's hit the key takeaways.
Okay, number 1. Rate equations are found by experiment. Never, ever from stoichiometry.
Number 2, a constant half-life is the undeniable fingerprint of a first-order reaction. It's your best clue.
And number 3, it's all about the rate determining step. The RDS dictates which reactants actually matter for the rate, and it's the key to unlocking the reaction mechanism.
And to leave you with something to think about, let's circle all the way back to the beginning, back to those picosecond lasers.
That progress, our ability to see these ultra-fast reactions, often comes from chemists using tools invented by physicists and refined by mathematicians.
Which raises the question, to what extent does the progress in chemistry really depend on innovation from these other fields to push our understanding of what's happening at that fundamental molecular level?
Something to think about.
It definitely is. We hope this deep dive helped clarify Chapter 22 for you. Thank you for being a part of our little last-minute lecture family.